So unit 6 is electrostatics. Electricity. Static means not moving. We're going to be looking at electrons that are stuck in place in this unit. In the next unit, we're going to look at circuitry, and all we're doing then is we're saying, hey, what if we give those same electrons a wire to go flowing down? What can we do then? And we start out with Coulomb's law. We're going to start off, hopefully, with a review of some of your Science 9. I hope. So matter is made up of atoms. We have a nucleus. What subatomic particles are contained inside the nucleus? Protons and neutrons. What's the charge on a neutron? No charge, right? Neutron walks into a bar and it says to the bartender, how much for a drink? The bartender says, for you? No charge, right? There's the punchline, okay? Electrons, what's the charge on them? Negative. Now, actually, Ben Franklin named them positive and negative, and he didn't know enough about electricity at the time. He named them backwards. He really did. Electrons should be positive because those are the ones that move around. The protons are generally locked inside the nucleus. Okay, we can now with our current technology get them to move, but it's way easier to get the electrons to move around. They're what move through wires. In fact, you're going to see when we get to circuitry, it's so much more convenient to deal with positive numbers that we're going to pretend protons are what's flowing through the wires, even though that's complete garbage. We're going to pretend that's the case. When atoms bond together to form solids, the electrons can be tightly bound to the atoms, as in covalent solids like glass. We call these insulators. Insulators can store or carry charge because they don't distribute it very well. They can also be free to move around, as in metals. We call these conductors. Remember your Science 9? Subatomic particles like protons, electrons, and neutrons have a property known as charge. And it is charge that is responsible for both actually electricity and magnetism. So some basic facts. There are two types of charge that we call what? What are the two types of charge? You know this, I already said it. That's too much writing. From now on, I'm going to abbreviate them. Now, I could just abbreviate it like that and like that, but I'm a math guy. Anytime I see a plus sign by itself, I go looking for an equation. To me, that's not an abbreviation for the word positive. That means add something. So this is my own abbreviation. I just add a VE next to the, you don't have to, but anytime I do that, I'll almost always go plus VE, positive, negative, negative, and that means the word positive, the word negative. That's me, Riley, being Mr. Dueck, really fussy about some obscure details. Probably you'll see most of the time they'll just abbreviate it plus and minus. Charge is measured in units of, who remembers from their Science 9, what do we measure charge in? Begins with the letter C. It's also in the title. Coulombs. Named after a scientist whose last name was? Coulomb, very good. Abbreviation, capital C. And charge is represented by the letter, sorry, it's not represented by the letter C. The letter C was taken already for the speed of light. It's C for constant, because the speed of light is a constant. So we can't use a letter C. So what we use actually is Q. Uppercase or lowercase. You know what? We're going to do the same convention as we did in the past unit with mass. If I have a capital Q, that'll be like a big planetary charge, a whole bunch of charge. A lowercase q, that'll be like in a little electron or a little proton or just a few little charges, but like the satellite. So capital Q, lowercase q. Why Q, you ask? Why Q, you ask? I'm so glad you asked. Another very important fact about charge is that it is, here's your fancy word, quantized. And yes, that's where the term quantum physics comes from. That's why the variable Q makes sense. What the word quantized means is that charge comes in a smallest chunk. Now, I need to update this, I just realized. Up until 2 years ago, what was the smallest chunk of money? The penny in Canada, okay? Now, I clearly need to change this, but for now, because the penny is such a nice number and it's a 1, the smallest chunk of money is the penny. You can't get smaller than that. There's no such thing in our society as half a penny. It may show up in the calculations. We ignore it. It turns out there is a smallest charge as well, the equivalent of the penny. It's the elementary charge. And the symbol we use for the elementary charge is a lowercase e. And the elementary charge, the charge on one electron, the charge on one proton, because those are the smallest fundamental units of charge, is 1.6 times 10 to the negative 19 coulombs. Someone double check me. I did that from memory. Matt, you have your formula sheet there? It is on your formula sheet. It's just below where all the planetary data is. It's on there somewhere, yes? Is it 1.6 times 10 to the negative 19? I don't know. Find elementary charge. I know. But this is my way of making sure you know where it is on your formula sheet. Fun will I make of you in like 2 weeks if you're like, where is it? It's there. Okay? Technically, plus or minus, positive if it's a proton, negative if it's an electron, and I really wish if there's one thing I could change, I would have said to Ben Franklin, call the protons negative, call the electrons positive. It would make the math. Anyways, I can't. All other larger charges are multiples of E. So Q, any other charge, is really N times E times 1.6 times 10 to the negative 19. Jacob, what that lets you do is figure out, if you know the total charge, how many protons are actually contained, or how many electrons are actually contained in this object. I got to be a little bit technical. Some of you may be aware of particles that are actually smaller than protons and electrons and neutrons, called quarks. And they have charges of 2/3 of an electron or 2/3 of the elementary charge and 1/3 of the elementary charge. So technically, that's not the smallest charge, but it will be here in high school. So it turns out you can break a penny up, but we didn't know that when we first set up this system. In this course, you're going to be provided with a data page. You probably already saw it in the gravitation section. You did, I hope. That lists the masses and the fundamental charge. So the elementary charge is 1.6 times 10 to the negative 19. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. Very small. The proton mass is 1.67 times 10 to the negative 27 kilograms. What is that? 10,000 times larger than the electron. Cole, can you do me a favor? Can you stand up and look in that silver pot and see if it's boiling? Yeah. Is it? Can you walk around and just unplug the pot? Unplug the heater, and then you can just leave it as is. Just unplug it first. Okay? And you can come have a seat. Those are the hot packet things. I think I brought them out during the work energy unit, right? No, I didn't? No. Okay, well. Apparently I sometimes forget some of the toys that I have. Back to here, you'll notice the proton is like, 10 to the negative 31, 10 to the negative 27, 10,000 times roughly heavier than an electron. An electron is really, 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 really light. Not only that, Sasha, we think perhaps that the electron has no size. Right now, its size is smaller than any technology we have to measure it. So we can tell you the size of a proton. We don't have any way of measuring the size of an electron, and the fact that an electron is kind of a particle weight, we suspect maybe it has mass, but it has no volume, no size, which is just the first in how strange electrons are. So the data page doesn't explicitly list the charges of particles, so you'll need to remember the following. The charge on an electron, negative 1.6 times 10 to the negative 19. The charge on a proton, positive 1.6 times 10 to the negative 19. And sorry, I should add the units, coulombs and coulombs. By the way, the fact that the elementary charge is so small means 1 coulomb has a whole bunch of electrons. In fact, 1 coulomb of charge probably would kill you. Certainly 50 coulombs would kill you. Okay. Neutron, 0 coulombs. And then also you can see the traditional abbreviations. We traditionally abbreviate an electron with an E negative, a proton with a P plus, and a neutron with an N0. Next page. For a conductor, the electrons flow freely and easily. For an insulator, the electrons cannot flow. However, the electron orbits can shift slightly. In fact, we call that polarization. But here is the key. Charges exert a force on each other. Charges exert a force on each other. Except unlike gravity, where masses exert a force on each other, it's not always attractive. So hopefully you learned in Science 9, like charges will something, unlike charges will something. Does anybody remember the words you used in Science 9? What do like charges do? Repel. Unlike charges will, the opposite of repel, attract. That sentence there explains an awful lot of electricity. So in this diagram, there would be a force that way. There would be a force that way. They would be equal in magnitude because forces come in pairs. In this diagram, there would be a force that way. There would be a force that way. They would be equal in magnitude because forces come in pairs. And what we're going to talk about today is, hey, how can you calculate how big that force is? It's going to turn out, Ryan, actually this unit, it's going to be an awful lot like the gravity unit, with the exception that sometimes stuff can fall up. Sorry. But you're going to notice a lot of the equations look really, 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 really similar to what we've just done, which is why I don't mind doing today's lesson. It's kind of like, oh, gravity in disguise. Example 4. Suppose you bring a negative rod and it's brought close to a neutral insulating ball. I wrote, the ball is first attracted and then repelled by the rod. Explain why this happens. And I forgot to get out the rod little demo, and it's locked up and I don't have time to go get it. But if you were to charge a rod, and the easiest way to charge a negative rod, like a plastic rod, is just rub it with some wool, and that tends to rub extra electrons onto it. And because it's an insulator, they'll just gather around the outside because they want to repel each other. So the way they can get as far away from each other is just to congregate all around the surface. So we'll show that this rod is negative like that. Now, that doesn't mean there's no positive charges. What I'm saying is there's lots of positive charges, but all of those positives are canceled out by a negative, and you got some extra negatives. And we're going to say that, let's zoom in a bit, Mr. Dueck. This ball here, let's make it neutral, give it 2 pluses and 2 minuses. I'm going to put a plus, a minus, and a minus. Now, when I bring this negative rod, when I move it to the right, what will the negative charges on the rod do to the negative charges inside that little plastic ball? Attract or repel? So what you're going to have then is this, negative, 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 negative. You're going to have the pluses move to the left, closer, and you're going to have the negatives move to the right, away. And so you have a net positive side of the ball. And that net positive side then will be attracted. But then they touch. As soon as they touch, what's going to happen is a few electrons are going to jump across because they want to go join those lonely little positives there. So you get this. You still have 2 positives, but now you've got 2 extra electrons to go with the original electrons that were there. And again, Jacob, instead of 2 extra, think trillions of extra, right? We're looking at our simplest case. Look at that plastic ball now. What's its net charge now? It's gone from being neutral to having a net negative charge. What's the charge still on the plastic rod? Negative. What will those two charges do to each other if they're both negative? Repel. And so you're going to end up with negative, 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 a couple of positives, extra negatives. We call this charging by conduction. Why conduction? Because you had to touch the ball to transfer charge. There is also a way to transfer charge without touching. We call that charging by induction. Okay. Generally, in all of our toys, we charge by conduction. That's what you're doing when you plug something into an outlet. Actual charges are running through it. We do charge things, though, by induction. Your electric toothbrush, if you have what is charged by induction, because we don't want water touching live electric contacts. And probably in 5 or 6 years, most of your cell phones will no longer be plug-in. They'll be laid down on a pad. You don't have to plug them in, and they'll charge by induction. Some already can. So let's look at charging by induction. Two uncharged metal spheres are fixed onto supports, and they're touching right now each other. A charged negative rod is brought in close to the spheres, and while the rod is still there, the spheres are separated. The rod is then removed. Show by a drawing how the charge is distributed in each diagram below. So beforehand, in our simplest case, Jordan, we're going to pretend we got 2 protons and 2 electrons on each one. Again, really trillions and trillions. Point though, they're neutral. But I'm going to bring in a what's it going to do to the negative charges in these 2 spheres? Attract or repel? What's it going to do to the positive charges in these 2 spheres? Attract. So you're going to end up with something like that. And again, I'm really simplifying. It's much more blurred than that. Then if we move this right-hand sphere to the right, while keeping this guy still here. And you notice we haven't touched the rod to these spheres. But if we move them to the right, so we still have negatives here, we'll end up with that. And if we bring the rod away, lo and behold, without touching the spheres with anything that was charged, we were able to separate charges. We call that inducing a charge. We call that charging by induction. And there's all sorts of other clever ways that we can do that. So it is possible to transfer charge, to move charge around without touching an object. Question, Callum? No. No? Okay. So if we're moving charges around, we must be exerting some kind of a force on them. Well, yeah, because like charges repel, unlike charges attract. How big is that force? And this gives us Coulomb's law. Coulomb found that much like for gravity, it's an inverse square of the distance between them. He found this. Electric force, and it's going to be a vector, is lowercase k Q1 Q2 over r squared. What equation does that look an awful lot alike? Callum. In fact, lowercase k is the equivalent of the 6.67 times 10 to the negative. The lowercase k is what's called a universal constant, and it is, hey, from your formula sheet, Matt, what is lowercase k? It's going to be somewhere below the big G in the electric stuff.
Like what the number is?
Yeah.
9 times 10 to the 9.
It's actually a nice constant. 9 times 10 to the 9th. What are the units?
Newton meter squared divided by Coulomb squared.
Oh, yeah, because look, if I got the k by itself, I have newtons on top. I'd have Coulomb, two Coulombs on the bottom, Coulomb squared, and I have meters squared. Who cares? I don't. It's the number that you need to put there to get an answer in newtons. It's 9 times 10 to the 9th. Q1 is charge 1. Q2 is charge 2. D or R is the distance between them. Coulomb, what did you say that this looks an awful lot alike? Newton's universal law of what? Gravitation. And this, for centuries, for at least 2 centuries, has had physics nerds pondering. And they've said the following. Well, if there's a fundamental charge, an electron, a particle of charge, an electron, is there a particle of gravity? We're looking for a gravitron. Haven't found it yet, but maybe. That's the first one. Second one is, if there's positive and negative charge, is there positive and negative gravity? Is there anti-gravity? Because, I mean, for Pete's sakes, look at how, wow, how symmetrical that is. That's different letters, but it's the same law. Nobel Prize waiting for you if you find it. Okay? So, to find the force in newtons, it's 9 times 10 to the 9th times charge 1 in coulombs times charge 2 in coulombs divided by r squared. Now, you'll notice I did put a vector there, but the vector is not going to come from the equation. We will decide the direction. How? Like charges what? Repel. Unlike charges attract. We'll always just decide either before or after the fact. And what that means is this. Well, to find the direction of the force, we're going to use like charges repel, unlike charges attract. Because we're using our knowledge of physics to decide the direction, we're not going to put negatives and positives in for the charge. If one's negative and one's positive, Jordan, all we're going to say is, oh, they're attracting each other. I'm not going to say that the force is negative. It's just attracting. Oh, and if both are negative or both are positive, I'm not going to put the signs, oh, they're repelling each other. Example 2. Find the direction of the electrical forces on the positive Q charge. So I don't know what the charge here is, but I know the other 3 are twice as big as the top left one. Okay? We have no way of analyzing this in one fell swoop. So we have something called the principle of superposition, and I'll write that word out later on. And what it says is, you know what? Look at 2 charges at a time, pretend the other ones don't exist. In other words, don't write this down, don't write this down. In your mind, do that. Don't do that on your diagram, but in your mind, do that. This is the charge that we're interested in. What direction will it feel a force from that guy? Will it be attracted down or will it be repelled up? Okay, so there's going to be a force that way. Don't write that down, but now I'm doing that in my imagination. What way will that top left charge feel a force? What direction from the top right charge? To the right or to the left? Hey, you know what? Let's get really, really clever. Let's call this charge 1, charge 2, charge 3. We'll call that force 1, force 2, and force 3. Okay, now I'm not going to scribble it this time. Imagine the the diagonal charges are gone, and only charge 3 is sitting there. What direction will it exert a force on charge top left? Will it attract it or will it repel it? Repel. That way. How could I find the net direction? I would add all 3 of those together, tip to tail, tip to tail, tip to tail. In fact, I think I'd get something like this. Down to the right, but I don't think it would make it all the way back. The reason is this distance is longer, so the force is weaker. I would end up with a net force of something like that. I think charge 2 would move diagonally slowly towards this guy. However, as it got closer and closer, this would be exerting a stronger and stronger and stronger repulsion force. Probably there'd be some kind of an equilibrium point where all the net forces would cancel out to 0 and it would come to a stop and just stay. So to solve force problems, we express the charges in coulombs. We substitute charges and distance into Coulomb's law to find the force. And we use the concept of like repel, unlike attract to find the direction. So technical comment, as I mentioned already, if we have unlike charges, one positive, one negative, then the answer that we get will technically be a negative answer. So if we actually put a positive and a negative into this equation, we'll end up with something less than 0. The significance of the negative just indicates they're being attracted to each other. We should not conclude that the force is negative. In other words, we should drop the negative when we state our answer. Instead, we'll say, oh, towards each other or attracted to each other. In fact, some people will write Coulomb's law with absolute value signs around the charges. I don't, but some people do. And you may, if you take physics next year, have to be that fussy and do that. So, let's find the force on an electron in a helium plus ion with a radius of 2 × 10⁻11. All right. Electrical force is equal to K, that's a terrible Q, Q1, Q2 over R squared. Very similar to gravity. What's K? Matt, what did you say it was?
9 times 10⁻⁹.
Much nicer than a 6.67 times 10 to the negative, but it's the universe we're in. Okay. Yeah, 9 times 10 to the 9th. Charge 1 is the nucleus. Look at the picture. What's inside the nucleus of a helium ion? 2 protons. What's the charge on 1 proton? What's the elementary charge, Matt?
1.6 times 10⁻⁹.
What would the charge on 2 of them be? Oh, you know what? The first charge is going to be 2 times 1.6 times 10 to the negative 19. That's this middle. The second part, second charge, is the electron. What's the charge on an electron? The elementary charge. Matt, what's the elementary charge?
1.6 times 10⁻⁹.
Technically negative. No, I said for forces, we're not going to put negatives. We're not going to put negatives in. Divided by, what's the radius of this atom?
2 times 10 to the 12.
Squared. What do you get? Yeah, crunch the numbers. What do you get? It's going to be small, but it's going to be a small number, but it's actually a huge force when you consider the mass of an electron. In fact, if you calculate the acceleration that this electron would be feeling, it's huge. Oh, by the way, what path is this electron tracing out? A circle? What force is pulling it in a circle? Not gravity, but electric force. Are you saying, Mr. Dueck, we could also go electric force equals circular? Technically, yes, but also technically no, because electrons really aren't particles that travel in circles. It's a good model that explains an awful lot, the Bohr model of an atom, but it's also total garbage, right? You guys have done, most of you, enough chemistry to pick that up. What do you get? Matt, what'd you get?
I got 1.2 times 10 to the negative 6.
Anybody else? 1.2 times 10 to the negative 6? Yeah, it's going to be small. Units. It's a force. Newtons. Newtons. Is that right, folks? 1.2 times 10 to the negative 6? It's 1.15, blah, 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 right? Although, I wrote here, although the force you calculated in example 3 may seem very small, we should note we're dealing with electrons, which has a very small mass. So just for kicks, I wanted to find the acceleration. So I said, well, acceleration is force divided by mass, and the mass of the electron is also on your formula sheet. That's your acceleration. 1.26 times 10 to the 24th. Humbly, I suggest that's big. How many G's is that? Honestly, about 1.26 times 10 to the 23rd G's. 23rd would be, oh, good gosh. We're well past trillion. I think it's around 1 hextillion or 1 octillion G's. It's a huge acceleration. Mr. Dueck, yeah? Doesn't that mean if the electron was traveling in a straight line at that acceleration, it would go faster than light? Only if it was able to accelerate for, let's say, 1 second. It can't. So don't worry, the universe is still okay. So, because you were a little sheepish, Matt, you're like, this seems really small. Actually, it's a huge force because the masses involved are so really, really, really tough for our brain to wrap around tiny. Example 4. I like example 4. I like example 4. Example 4 is a nice question. Now, I already told you that 1 Coulomb of charge is huge, would probably kill you. Certainly 50 coulombs would kill you. But 1 electron is ridiculously small. What we're going to be dealing with most of the time in this unit are micro coulombs. So put a little arrow here, make a little note. This is micro coulombs. And anytime you see that, and you're going to be seeing that time and time and time again, oh, what can I replace that with? It is also on your formula sheet where I have all this scientific notation prefixes. There's a chart there somewhere. What's micro? 10 to the what? Roy, what's micro? 10 to the what? Yep. You'll end up memorizing this one because it's literally going to appear in 90% of the questions. But if you blank, it's on your formula sheet, okay? Now, we want to find the net force on that guy. But there's 2 charges exerting a force. Once again, we're going to use the principle of superposition. Don't write this next bit down. I'm just going to do this in my mind. Ignore that. Don't scribble it out. You know what? Let's call this charge 1, charge 2, and charge 3. So let's call it Q1, Q2, Q3. Normally I go from left to right, but since charge 1 is what they wanted me to find the force on, I said, why don't I call that the number 1 charge? Whatever. Okay. So the first thing that I'm going to do is I'm going to find the force between charge 1 and charge 2, magnitude and direction, which is going to be K Q1 Q2 over R squared, which are the radius between 1 and 2. K is 9 times 10 to the 9th. There's our constant that we need to do the adjustment to get it to newtons. Charge 1, 1 microcoulomb. 1 times 10 to the negative 6. Anytime you see that micro symbol, times 10 to the negative 6. How big is charge 2? Look at the diagram. How big is charge 2? Really? Look at the diagram. How big is charge 2? How big is charge 2? Can we see where that is? Yes, 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 yes. But Although Mark said negative. No, 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 no. 1 times 10 to the negative doesn't go in the equation. Divided by what's R? Don't say 20. Careful. 0.2, right? Centimeters squared. And I'm going to carry this to a few extra sig figs, because what I'm going to do is I'm going to find the force between these two guys. I'm going to find the force between 1 and 3, and then I'll add them together. But they're vectors. I'll have to add them together vectorially. I'll have to go kind of a winner minus loser dealy. So what do you get? Let's see here. Oh. Forgot the scientific notation. Do you get 0.225? Okay. Microcoulombs give us, Matt, better numbers than that 10 to the negative 6 a couple of questions ago that was kind of freaking you. They give us little easy numbers that we can kind of wrap our brain around. Units. What did we just find? Units?
Oh, newtons.
Newtons. Direction. Look at charge 1. Is charge 2 pulling it to the left, attracting, or repelling it to the right? Look at the picture. I want an answer, left or right?
Left.
Left. Now we do the same thing, but this time in my mind, I cover up that guy. I find the force between charge 1 and 3. I don't care about the force between charge 2 and charge 3, because Joel, this question said, find the force on the middle charge. Okay, it's only 2 charges acting on it. With me? On your own, it's going to be K, Q1, Q3 over R squared, which are the distance between 1 and 3. On your own, try doing this. I'll do it up here. Let's see if we end up with the same thing. And don't forget to then ask yourself, is charge 3 tugging charge 1 to the right or repelling charge 1 to the left? What do you think about that? Mr. Dueck, yes. Can I use that same trick of just backspacing and editing? Yes. That's a 2. That's a 1. You get 1.8? Yep. Direction. To the right or to the left? What you're asking yourself is, are they like charges repelling each other, or are they unlike charges attracting each other? And our frame of reference is we're looking at the middle charge. Which way is he going to want to move because of the right-hand charge? To the right? How will I add 1.8 newtons right plus 0.225 newtons left? Someone said it. You're right. Yeah, I'm going to have to go winner minus loser. Hey, what if they were both to the right? What would I do with these numbers? What if they were both to the left? Add. And in this case, I can already tell you the net direction. Which is the winning force here? Right. You know what? My final answer is going to be to the right. So F net is going to be 1.8, take away 0.225. And I get 1.58. I'll go to 3 sig figs now. What did you say the direction was, AJ? To the right. Okay? I like this question. I like this question. I like this question. Absolutely a fair written question. I'll give you 3 charges in a nice straight line. I'll say pick one of them and tell me the net force. Okay. Turn the page. A couple more, we're done. And then I got some cool videos to show you. At which point, approximately, could we place the 1 microcoulomb charge so that it would experience no net force? So look at this picture very carefully. What's the charge on the left-hand charge? You all turn the page now? Look at that picture very carefully. What's the charge on the left-hand most charge? What does it say? What's it labeled as? Negative 1 microcoulomb. What's the charge on the right-hand charge? Okay, so both are negative and the right one's twice as big. Right? Okay. Where could I put a charge so that it would experience no net force? You know what? Let's just walk through each possibility. Now, we're putting a positive charge. Suppose I put a positive... Don't write this down just yet. We're just going to do a process of elimination. Suppose I put a positive charge right there. What direction would it feel a force from the left-hand charge? It would feel a force that way. What direction would it feel a force from the right-hand charge? Let's call this charge 1. Let's call this charge 2. What direction would charge 2 tug my test charge? Can to the right plus to the right ever equal 0? So what you can do is pick up your pencil and you can go, nuh-uh. Let's try looking at situation B. So let's put our little positive test charge right there. It's a positive. Which way, what direction will it feel a force from charge 1? What direction will it feel a force from charge 2? Which charge is bigger? Which would mean it would exert a bigger... Oh, but which charge is closer? The smaller charge is closer, the bigger charge is further. Hey, maybe that might be enough to balance out and have them cancel, because I certainly have left plus right. You know what? I think B, I'll come back to it. Let's test the other ones. C is weird. What direction would a charge right here feel a force from charge 1 if I put a positive right here? That way? What about charge 2? If I add those two together vectorially, can I possibly get a 0 there? No. So what you can do definitely is pick your pencil up and say, nuh-uh. D is possible. Let's see. If I sit right here, what direction will charge 1 be exerting a force? What about charge 2? Which force would be bigger? You know what? Since charge 2 has a bigger charge and we're closer, you know what? I don't think that can be in balance, even though in theory the directions cancel. I'm pretty sure the answer is B, but let's check E. What way would charge 1 exert a force on a positive right here? What about charge 2? Oh, can left plus left ever equal 0? B. And you know what? There's my we did a good explanation. I probably wouldn't give you this question as a to explain is a lot of English. I would feel okay with example 5 here as a multiple choice nasty. This is also 3 charges, but are they in a nice straight line? No. You know what? We're going to do the same strategy as we did right here. We're going to use that principle of superposition. I'm going to ignore one charge, but I think I'm going to end up with 2 vectors that I'm going to have to actually add tip to tail and do some trig. Let's call this, oh, here's the electron, so let's call this charge 1, charge 2, charge 3. And these are all microcoulombs, oh, and micrometers. So wherever you see the micro, replace it with a 10 to the negative 6. All right. Let's find the force between charge 1 and charge 2. That's going to be K Q1 Q2 over R squared. It's going to be 9 times 10 to the 9th. Charge 1. It's an electron. I will never tell you the charge on an electron. It's an electron. It's on your sheet. 1.6. Technically negative. Oh, but we don't put negatives in for here. We decide the direction ourselves. Charge 2. 1 microcoulomb over the distance between them, 2 micrometers squared. You get 3.6 times 10 to the negative 4? Direction. Which way will that electron want to move because of that Q2? Will it be attracted towards or repelled up?
Attracted down.
Okay, let's call that let's do the same thing. Let's find the force between charge 1 and charge 3. It's going to be K Q1 Q, not 2, Mr. Dueck, 3 over that radius squared. It's going to be 9 times 10 to the 9th. It's an electron. Hey, I think I can backspace and just change like, oh, sorry. I put a 1 there instead of a 2. I was going to say I just got to change one number, but I forgot to change the number when I wrote it. A 2 there. In fact, I could do this in my head. I think it's going to be 7.2 times 10 to the negative 4 because it's going to be twice as big, isn't it? Everything else stays the same. It's the same radius, right? Right? Yeah, 7.2 times 10 to the negative 4. Direction. Which way will the electron want to move because of charge 3? To the right, east, or to the left, west?
East.
To the right? So this negative electron wants to go to that negative charge there? Ah, repel, yes? So Newton's west. Sorry, question?
No.
Okay. Hey, how will I add those two forces together now? Draw them. Can do that. And it's going to be a nice right angle. It's actually not going to be too bad. So it's going to look like this. Yoink. 3.6 times 10 to the negative 4. Yoink. About twice as long. 7.2 times 10 to the negative 4. There's the force. I can use Pythagoras. That squared plus 3.6. Oh, we should probably put that in brackets. 3.6 times 10 to the negative 4th squared. Square root. 8.05 times 10 to the negative 8.05 times 10 to the negative 4. Is that right? Newtons? That's the magnitude Direction. I guess that'll be theta right there. By the way, that theta right there is what of what? North of south, east of west, what of what? It's either south of west or west of south. Which one?
West of south.
Jordan?
West of south.
West of south, right? South of west would be go west and then go south. West of south, west. Dope. West of south. Let's find theta. Opposite. Oh, good gosh. Which trig function? No sine law, no cosine law. Which trig function? Tan. Opposite. By the way, if you were like me, naturally really lazy, you could actually just go shift tan of 2 over 1, because that's what that reduces to. You get the same angle as you guys got by typing the whole thing in, yes? No, yes? Someone try it? Anyone? All right, shift tan of 7.2 times 10 to the negative 4 divided by 3.6 times 10 to the negative 4, and lo and behold, holy smokes, 63 degrees. At 63 degrees west of south. Coulomb's law. Humbly, I suggest, looks an awful lot like gravity. Well, there's a reason. Just like gravity sends out a gravitational field to tug other masses in, masses send out gravitational fields in all directions, charged objects send out electric fields in all directions, and that'll be the next lesson. What's your homework? To study for the test, but what's your homework for next week, Thursday? I think number 1 is good. No, you know what? That's way too much of the same old, same old. Let's do number 2. Five is good. Seven is good. 8 is good. Nine is cool, but way too tough. 9 is an equilateral triangle. By the way, if it's an equilateral triangle, what's every single angle inside there? Equal, more specific. 60 degrees. And that would be like all sine law, cosine law. We could. Forget it. 10 is I'm fair game with. Now 10, notice it's a proton. Hey, what's the charge on a proton? 1.6 times 10 to negative 19 as well. So it's going to be very similar. Oh, 2 electrons. What do they act on 1 proton? 11 is good. 12 is overkill. 13 is overkill, but cool. Yep.